Now we are going to address the last topic for this chapter, that is called the vertical shift. If you remember, last experiment was about lateral shift, sideways shift. Now this is vertical shift. If you call this sideways shift, this is called vertical shift. Now for that, first you need to understand why we need this vertical shift. So there is a formula provided in your textbook, that is for refractive index. We already know from your theory that refractive index is given as sin I by sin R. We covered it in our first experiment. But there is another formula. The formula is thickness of the glass slab by thickness minus vertical shift. So thickness of a glass slab is straightforward. I can measure this thickness with a scale, but vertical shift we have a procedure. But before we do vertical shift, I want you to observe something. I want to pick something symmetric. See, I am drawing alphabet B over here. I am trying my best to keep it perfectly symmetric, as you can see, right? Now, if I place this glass slab midway, now observe these two lobes of B. Both are almost the same size because they are appearing at the same distance from your eyes. But what if I cover this glass slab in this way? Please tell me which lobe of this B is appearing closer to you. Observe carefully. The lobe that is covered by the glass is appearing closer, whereas the one that is passing through air, the rays from this portion is passing through air to your eyes. The rays from this portion is passing through glass towards your eyes. The one through glass appears closer, the one through air appears far away. This gap between the glass image and the air image is called vertical shift. You might have seen such a thing on many offices. Like the office desk of some people, they keep such glass slabs. So they just place it on an alphabet or a word or a letter and then try to read it. So it's easier to read because they are making use of this vertical shift concept. In real world examples, what you can have from your textbook example is, imagine a bird is flying on top of a river and a fish is underwater. Due to the help of vertical shift, the bird can see the fish in a very big enlarged way. So it can dive into the water and catch the fish easily because it has this zoomed in version just like the base of this bee. Okay, so that is a real world example, and practical example I've already given you. People keep them on their office tables so they can read everything in a much more clear way. By the way, this is not a magnifying glass, it's just a glass slab which is helping us with this vertical shift concept. Now I want you to observe the process of finding vertical shift on a paper, and so that once you find that vertical shift, we can substitute in this formula to measure the refractive index. Let's try to recollect. Refractive index of the glass slab, the semicircular glass slab from the first experiment was around 1.5. Let's see what value we'll get now. So let's go ahead for the next step of this experiment. Right, so for this experiment, we are not going to use this whole thing as the thickness of the slab. To have simple vision, easier vision, we'll use this as the thickness of the slab. So what I'm doing is, I'm placing this rectangular glass slab on the paper and I'm going to draw the boundaries in this manner. Just like before, I will label these edges or the vertices as A, B, C and D. The next step is, I need to extend this BC line. From C it has to extend till 15 centimeters. So I have a scale over here, as you can see. First step is, I will extend this a little bit. Then I will extend it further. So first a little bit of extension to make sure that it is in a straight line. Now I am placing the 0 centimeters at the vertex C, and I'll extend this line further until 15 centimeters distance. You might be wondering, why 15 centimeters? Why not 20, 25 or 10? So I exactly do not know the reason, but my prediction is it is good enough distance to have a clear vision, and it is also good enough distance to avoid strain on your eyes. If the distance is too far, then you can't see it clearly. If the distance is too close, too small, then it might cause strain in your eyes. It will cause discomfort. That is the reason we are doing this. Now, the next step is I am going to place this rectangular slab back on ABCD. Now, I am going to use 2 pins, one facing each other at that 15 centimeters mark. I am not poking the pins, by the way. We are just making them sleep horizontally. Now the idea is you have to observe in such a way that your eye is exactly, one eye should be open and it should be exactly at this edge of this glass slab. The reason we do it is we want light rays from this pin to travel through air into your eyes, and light rays through this pin to travel through glass into your eyes. So when we do this, we will observe that the glass pin appears closer, whereas air pin appears far away. The next steps are adjusting in such a way that both pins will appear as if they are making a straight line. So let me show you what I mean first here. Then I will try to show you using a zoomed in version. Let's say I keep it very close, the air pin. Now clearly for me the air pin is extremely close. Now I want both of them at the same location. So I'll keep moving it, and whenever I feel they are approximately at the same distance, I will stop. I still feel air pin is close to me. So I'll move it further, further, further. I still feel air pin is a little close than the glass pin. Now I feel they both are almost at the same distance. So this is where I need to stop. Now I want you to experience this through the camera. I will project it towards you and we can continue. Observe, the light rays from this pin are traveling through the glass, whereas the light rays from this pin are traveling through air towards your eye. Check carefully, the glass pin is appearing a little closer, a bigger, whereas the air pin is appearing a little far away or smaller. So what I am doing now is I will bring it too close. Now check, which one appears closer to you? Air pin. So I will move it back until you feel that both are almost at the same location, or they're approximately making a straight line. So even now you might be seeing air pin closer and glass pin far away. So I'll move it further and ask you again. Now check, still the air pin is closer than the glass pin. Now around this region you might feel that they're coming close to each other. I'll move it further, further, further. And now please check, approximately at this region, they might appear almost like they are making a straight line. Now let's check from the top, the gap between the two pins. Check the gap between the glass pin and the air pin. The tiny gap that you see is called vertical shift. On this line, I'll just make clear points for those two locations, and I'll put them away. This gap is the vertical shift. Let's measure what is that distance. We do not need the glass slab. Now if you check carefully, that gap is around 0.6 centimeters. So vertical shift is 0.6 centimeters. Simultaneously, let's check the thickness of the slab. Glass thickness, I want you to see this. Place the glass slab again flat on the surface and then measure its thickness. Put 0 centimeters on one corner and check the other side. It's approximately 18 centimeters. 1/8. I'm sorry, this is not 0.6, it is 6 centimeters, and whereas this one is 18 centimeters. So with that we are done with the inputs. Now let's substitute these numbers in our refractive index formula to close this topic. As we have just seen, vertical shift is 6 centimeters and glass slab thickness is 18 centimeters. Let's substitute these values in the formula. Refractive index is thickness, that means 18 divided by thickness minus vertical shift, that is 18 by 12. 6 times 2 is 12, 6 times 3 is 18, 3 by 2 is exactly 1.5. Refractive index does not have any units because you have centimeters in the top and centimeters in the bottom. It gets cancelled out. So observe carefully, refractive index is 1.5 again with a different method. So we found out vertical shift. It is the gap between the light traveling from air and the light traveling from the glass surface, and the refractive index which matched exactly with our previous result. Thank you.